Namaskar and welcome back to the course on statistical mechanics of phases and phase transitions. We are working on the chapter on approximate methods that can be applied to the non-perturbative regimes of coupling constants, and in this context we looked at several problems. We looked at the lattice gas model and showed that there is a connection between that problem and the Ising model, and we use that to study the liquid gas transition. We briefly explored superfluid transition in helium-4. We studied Bose condensation of a Bose gas in arbitrary dimensions and found that you will get condensation only in 3 dimensions, and condensation can be modeled by a broken U1 symmetry, and this U1 symmetry corresponds to the conserved total particle number. So today what I am going to do is I am going to discuss the physics of mixtures of helium-4 and helium-3. So briefly let me revise the phenomenology of helium. So helium is an inert atom and it comes in 2 isotopes. The first one for helium-4 is a boson and helium-3 is a fermion. If you take helium and cool it down at ambient pressure, if you cool it down below 4 Kelvin, it goes to a usual fluid with usual properties. So in this field it is called as a normal fluid. So you will get a normal fluid, and if you go even further down in temperature at about 2.2 Kelvin, it goes to a superfluid which has exotic properties like zero viscosity, it can flow through pores, it can climb walls, and it can do all kinds of magic. So what we understand today is that superfluidity can be modeled as a set of interacting bosons, although we worked with a simplified model of non-interacting bosons. If you work with interacting bosons, you can fairly well describe this phenomenon of superfluidity. Okay? Alright. So what we had discussed was a mixture of pure helium-4 atoms. So they are just a collection of bosons, and we believe that our toy model of Bose condensation of ideal Bose gas will do the job of at least getting some qualitative idea of what is going on there. So in the meantime, people thought about what happens if we mix a little bit of helium-3, which is fermions, mind you, which are fermions, into a collection of helium-4. So this question has a lot of interesting physics as well as very important applications which I will not get into. So let me start by reviewing some of the known experimental results. Okay, so what I have here is a plot of the concentration of helium-3. So it starts at 0 and goes all the way to 1, and this axis is the temperature. So let us start with something we are very familiar with. So suppose I have no helium-3 atoms in my system. So if I start from a very high temperature and cool down, I will below 4 Kelvin I will have a normal helium-4 liquid, and then when I hit 2.2 Kelvin I will undergo this lambda transition and become a superfluid. So this region is pure helium-4 which is a superfluid. Okay. Now let us say that I have 5% of helium-3 mixed into the helium-4 gas. So now when I start coming down, I will still have a simple, I will have a liquid, normal liquid, which will then undergo a lambda transition, mind you now is at a lower temperature than what it was when I had pure helium-4. So it keeps undergoing this lambda transition until certain stage where you hit, where something else shows up, and if you show up here then it actually phase separates. It separates into 2 2 different fluids with different concentrations of helium-3. So what you will have is you will have a helium-4 rich fluid, so that will be the fluid on this side, which will settle down in your, if you are doing it in some devoir of some kind, it will settle down in that, and then it will form a meniscus, and there will be another fluid which is the lighter fluid which is helium-3 rich and therefore has lower density, and it will float on the other side. It will float on top of this, this helium-4 rich liquid. So this is what is observed, and these experiments are incredibly beautiful experiments. And so what happens is that this lambda transition line, as you come down, it ends here, right, and there is some statement here about triple point and all, which we will see what all that stuff is. And so there is a phase separation line, and this is called the miscibility gap. So here helium-3 and helium-4 will not mix at arbitrary proportions. So you can see that here it mixes at arbitrary proportions, it remains normal in this regime and superfluid in this regime. Okay, so this is what we know from experiments, mind you, right, that is we have not made any theory about this and so on. Okay, so now comes the question of how do we model a mixture of helium-4 and helium-3. So you might think, okay, well, these are really quantum mechanical problems, so I should think about some quantum setup and so on. But you know, so perhaps sometimes doing something very complicated is not what you want to start with. So Bloom, Emery and Griffiths, these 3 physicists, quite a while back when these experiments were very current and people were thinking about these problems, they addressed this question of trying to get this kind of phase diagram from some model, believe it or not, in a purely classical model with Ising symmetry. Okay. So by now you should not be surprised that Ising symmetry is going to help us do this, because you see we saw that the liquid gas problem, which did not have any apparent Ising symmetry, you can map it to some problem with Ising symmetry, or some Ising like variables at least. Okay. But the question is, we saw in the last meeting that the order parameter associated with superfluidity would be something like a complex number. So this is what I had mentioned last time, that we are going to use the 2 ideas, namely lattice gas model of liquid, liquid gas physics, that kind of stuff, and the idea that superfluids have this complex order parameter. But how can I simply implement this complex order parameter here? Okay. So what Blume-Emery and Griffiths did is they came up with an extremely clever way of modeling the superfluidity, or let me not say superfluidity, the superfluid state or the condensate state, let us say. So what they did was they said that I am going to think of some kind of lattice gas or some kind of Ising model where I am going to place a spin 1 variable at every site. Now what do I mean by spin 1 variable? I have to clarify this. Spin 1 variable is a variable Si which takes one of 3 values. So it can take -1, 0 and 1. If it had taken only -1 and 1, we would say that it is a spin half variable. So recall from your study of quantum mechanics that if I have spin S, then there will be 2s plus 1 Sz states, and so you can think of these -1, 0, 1 as the Sz states of some spin 1 system. So now you will say, okay, where am I getting the spin 1? So the interpretation of spin 1 is the following: if the spin configuration at a site is plus or minus 1, then we say that there is a helium-4 atom sitting there. You get that? So it is plus or minus 1, then there is a helium-4 atom sitting there. If it is 0, we say that there is a helium-3 atom sitting there. So every site will have one of these variables, right, by one of the values of these variables +1, -1, 0. So you can see that I have just plotted some random variable random configuration like this. So the the greenish color is +1 and the bluish color is sorry, oh there is a mistake. So you can just say the blue color is -1 here. So the green is +1, this is 0 and this is -1. So this is the kind of configuration that you have. But you are now left wondering, I am looking for a superfluid, so how can this help me? So here is the rationale for believing that this could be a good model for helium-4. So note that the state with +1 and -1 are both states corresponding to having a helium-4 atom. If I have a helium-4 atom, then if I am in a superfluid phase, it is associated with some phase that the full wave function has picked up. Now typically that phase would be some complex number, unimodular complex number. So what Blume-Emery-Griffiths are arguing is that I am simplifying the problem of assigning phase to the superfluid order parameter by saying that instead of taking any arbitrary phase on the unit circle in the complex plane, I am only going to allow it to take two values, one of two values of phase, namely phase is 0 or +1, e to the I theta equal to 0 is +1 and e to the I theta equal to pi, which is the 180 degrees from this point. So the idea is that this U1 symmetry is kind of simplified to a Z2 kind of story. So the phase, the superfluid will pick either 0 phase or -1 phase. This is the rationale for placing for giving these values +-1 values. It is to capture the fact that the original problem that you wanted to model had this U1 phase, and you are trying to simplify the description of this U1 symmetry breaking by allowing one of two values of the phases rather than the infinite, uncountably infinite possibilities. Now you can legitimately question whether this works or not. Okay. So how would you check whether you have got superfluid or not? So for example, if you find that the average value of SI after you have done the calculation is 0, that means that these phases are fluctuating randomly and therefore you have not condensed. On the other hand, if you find that SI is not equal to 0, expectation value of SI is not equal to 0, then it is an argument to say that there is some kind of condensation because your system has picked up some particular phase, and that is what is the idea of this model. Okay, I hope you are able to appreciate that while this may appear drastic, it seems to have a semblance of some physical aspects of condensation have been captured by this kind of setup. Okay, so what we have done now is we have identified a set of configurations of some kind of spin variables which can take +1, 0 or -1 values at each site, and you give me some you specify one of these values at each site and then take the collection of those variables at each site, and that defines a configuration. What else do I need? Once you give me a configuration, I have to write down a Hamiltonian to be able to model some physics, some statistical physics of this problem and whatnot. So how do we write down a model for this? So this is the idea. So I am going to walk you through this. It looks fairly complicated, so please do not be intimidated by it. It's we will look at each of the term and understand what this is. Okay. So what we have is, on some d-dimensional cubic lattice with n sites and periodic boundary conditions, given this configuration of spin 1 variables at each site, the energy associated with the configuration is given by this humongous looking expression. So let me walk you through each of the terms. So you will see that there are terms of the kind Si, Sj. So, there are terms which are linear in S, right. There are terms which are quadratic in S as well, Si square. Now, this is where the difference between our old Ising variable where S took +1 and -1 and this kind of spin 1 Ising variables becomes immediately evident. So, for example, if I took my old Ising variables, the usual Ising variables which take only +-1 values, the square of such Ising variable will always be +1. So, it gives you nothing more than just a number. So, if you write down a term in your Hamiltonian where there is an Si square term, it will just shift the energy by some number, but it will not give you any additional physics. Here Si square can take different values. So, for example, Si square will be +1 if it is Si is plus or minus 1 and 0 if Si is 0. So, it will not always take just one value. Now, if you by just thinking about the statement that I made, you will realize precisely that Si square at a site will give you the number of helium-4 atoms. So, if say Si is +1, that means there is one helium-4 atom there. Similarly, if Si is -1, that quote unquote atom has a different phase, whatever that means, but the square of that is the number, right, and that will give you this meaning of Si square to be the number of helium-4 atoms at a site I. Okay. So, what does this term tell you now? This term, okay, let me go through a little bit more. So, Si square will tell you the number of helium-4 atoms at a site I. So, what is 1 minus Si square? This is also very easy to see. So, for example, if Si square is equal to 1, then this number will turn out to be 0, which means it is counting the number of helium-3 atoms. So, if Si square is 0, then that is what we have assigned it to be helium-3, and 1 minus Si square will be 1, expectation value will be 1, and that will give you the number of helium atoms is 1. So, this is the operator or the term that gives you the number of helium atoms. With this insight, we can understand what each of these terms are. So, what this does is the following. It goes to nearest neighbor site I and j, it finds the number of helium-4 there, and it says that if I have 2 helium-4 atoms on the neighbors, their energy is changed by this term V44. That means it is the interaction between helium-4 and helium-4. Okay? Alright. That is what this V44 is. V33 is the term that tells me that if I have helium-3 atom on one site and helium-3 atom on the neighboring site, what is the energy that I will have? That is V33. Okay? And then I will have V34, which is the interaction if I have one helium-3 and one helium-4 on neighboring sites. So, that settles these V terms. Okay. So, what are the other terms? So, what is this term? So, this is our usual Ising term, like an exchange term. So, what does this try to do? It tries to make sure that the phase of bosons on neighboring sites, remember Si by itself is like the phase of the boson. It wants to make sure that they are same, assuming that J is positive. So, this is what this is like a Josephson coupling, right. So, Josephson coupling tells you that if you have a gradient of phase, then it will cost more energy for you, right. So, this is what this J comes, this is where the J comes from. Okay. Now, you have two other terms. The two other terms will help us fix the number of bosons etc. and fermions. So, there is a chemical potential associated with the bosons and that is written as mu times the number of bosons, and remember Si square gives number per site of helium-4 per site. So, it just sum of all that will give you exactly that, and this is precisely the number of fermions, and mu3 times the number of fermions. Okay. So, I have walked you through all this hopefully, and I am sure that you will find that there are so many parameters in this, and this looks fairly complicated. So, however, what on earth chance do we have to solve some problem like this? Okay. So, what you have to now do is take a pen and paper and look at those expressions, and you can manipulate them, and you will be able to see that you can group the terms into a few sets. Okay. So, there is this exchange term SISJ that just has showed up here. All the V terms that were there, they can all be combined together and they can be written in this fashion. And if you have just worked all this out, you will find that this V term here will be V4 plus V44 plus V33 minus 2 times V34. So, roughly this quantity is the sum of interactions of helium-3 with itself, helium-4 with itself, minus twice the interaction between helium-3 and 4. Okay. Now, you will see that this delta term, which is proportional to Si square, has picked up mu3 minus mu4 expected, but it has also picked up some terms associated V33 and V34, and the reason for that is this term which talks about the interactions between helium-3 and helium-4 on neighboring sites will also produce for you, when you expand this out, terms corresponding to the linear terms in S square. You will get linear terms in S square when you do that. Okay. All right. Now, I have to emphasize here that I have also added one term which was not there in the previous transparency, and this is for illustrating some ideas later. And this is some field. Okay, I shouldn't say magnetic field, it is some field, and let us just think of it like a device to study some phase diagram or something. We will not explore what exactly it means at this stage. Okay. So, now first thing is, you will realize now that if I set this H is equal to 0, if I set this external field that I have applied to 0, and I have only these 3 terms in the Hamiltonian, you will see that this system has a global Z2 symmetry. And what is how does that symmetry show up, or how do we implement that symmetry? The idea is that you take the set of SI variables and change the sign. So, what happens is, if I have plus 1 at a site, it will go to minus 1. If I have 0 at a site, it remains 0, and if I have minus 1, it will become plus 1. That is what is the meaning of this statement. So, roughly speaking, I will change the phase of the fermion to the other phase. So, I have only plus and minus 1 phase, and if I have I will change the phase of the boson if I have if it has plus 1, it will become minus 1, it will become plus 1. If I have fermion, I leave it alone, I do not do anything to it. That is why it is 0 remains 0. Okay. So, now we have to analyze this Hamiltonian. So, we are in the regime of trying to, or we are in the place where we have to try to solve such complicated models. Now, it is a good idea to now start discussing some things about the parameters and so on. So, a priori there is no way to say that any of these parameters are big or small. You have to have some experimental data, and if you look at the experimental data, they will, they can be comparable and so on. So, there is no small parameter here. H is some tool which we have, H is some term that we have added, we may be able to control that, but other than that, these are all some parameters of helium. So, the question now is, which approach would you want to choose? Do you want to choose mean field theory, or do you want to use Feynman variational principle and so on? So, if you look at this expression and try to see which of the methods you will want to choose, you will see that the Feynman variational principle is going to be a bit more you have to have some imagination to come up with some trial Hamiltonian, you have to know what kind of parameters to have in that and so on. So, if you do not have experience in this kind of problems, it may not be easy for you to guess a Feynman variational Hamiltonian. But you will see from our discussion, all the formal discussion we had about mean field theory, you will be able to see that those formulations can be directly brought to bear on this problem immediately without too much difficulty. Okay? So, this is what we are going to do. We are going to do the mean field theory of the BEG model. So, let us try to see how to do the mean field. So, I have the Ising term, the usual Ising exchange term. So, I am going to replace that by some mean field times the spin, right. And in taking the product of the Si Sj and making decomposing that using the mean field decomposition, I have also made the ansatz that the mean field value of Si at every site is the same. That means I am saying that the state I am looking for does not break translational symmetry. So, I have this quantity Si mean expectation value of SMF. So, I put that here and then I will have these two terms that I had, and you will see that those two terms will end up producing a term such as this delta times. So, delta is just the linear term in S square. So, that is not done, there is no mean field here. So, the first different mean field that I am going to do is than what we did for the Ising model previously is this one. So, this looks like an A times B term, like what we had discussed in the mean field theory formulation. So, what you do is you write this term as the expectation value of S square times S square j plus expectation value of S square j times Si square minus the expectation values of these two things together, taken product together. So, once you do that, you will get a term that looks like this. Z has come up and Z is the coordination number, which I mentioned briefly here. I probably did not mention, but it is the coordination number, right. So, that is what you will end up getting. After you have done all this, you will also get some constant terms. For our immediate discussion, they are not immediately important. Of course, to find which state has lowest energy, etc., you have to keep them in the calculation and deal with them carefully, right. Okay. So, we have used this translationally symmetric ansatz and we have reduced the problem to you see now they have become problem of single site. That means that they are non-interacting. You have got a problem where the spins are not talking to each other, they are all isolated spins, right. Okay. Now, what I do is I set up the self consistency equations. How do I set up the self consistency equations? So, let us go through that a little bit. So, what I am going to do is just to be consistent or just to be connecting to the previous solution of our simple Ising model, I am going to call this S mean expectation value of S mean field as M, something like magnetization, and we also note that expectation value of S square mean field should be equal to the number of helium 4 atoms. So, in fact, this is the condition on our the amount of helium 3 we have added. So, X is the fraction of helium 3. Okay. Now, what you have to do is you have to take this Hamiltonian, and I leave this as an exercise to you. You have to compute the expectation value of a variety of things in this Hamiltonian, and you have to write the equation self consistently. That means the expectation value of this Si operator that I get from this should be equal to M. So, that is, so I compute the expectation value of Si from this expression of the Hamiltonian and the partition function associated with that, and I will end up getting this self consistency equation. So, I will get two self consistency equations, one which says that 1 minus x is equal to this, and the other one is this. Now, in these expressions you will see that there is a quantity called as delta prime. This delta prime is related to our original definitions of things. So, that is delta minus z times v minus x. So, you see this z square as s square has been written down as 1 minus x, and that is where you get delta prime. Okay. So you will see that these are fairly complicated equations. If it is only one of them, then you can get away with it. So now you see this 1 minus x is there, and you see this delta prime has 1 minus x in it. So you see that you have to work on this a little bit. But it turns out that there is a very interesting simplification that takes place when you look at some reasonable numbers for v and so on. So what is the reasonable simplification that takes place? V, remember, was this quantity. So it turns out that the sum of these two is roughly equal to the sum of this is twice equal to V34. So you can set V equal to 0. So if you set V equal to 0, then this set of equations simplify quite a bit, because what happens is that this equation does not depend on x anymore, right. It does not, the top equation does not depend on x, and this becomes simply an equality. That is, if you find an m that satisfies that equation, you just stick it in here, you will get 1 minus x. So this is also a very useful you can say approximation, but okay, we have to check whether we get the connection, we will be able to connect correctly with the experimental data, and that will hopefully settle the issue. So what I have in these equations finally is that this, I will use the value of delta instead of delta prime to solve these equations. Okay, let us see what is the solution we get. So remember, so before we do that, let us remember what are the parameters that we have. The parameters that we have in our theory are J, right, the exchange coupling. We have set V to 0, there is delta, and we have temperature. These are the parameters that we have. So how are we going to study the phase diagram? I can use dimensionless quantities, something like T by J and delta by J, and work with those. So the natural scale here is Z times J. As you see in that any of these kind of mean field theories, you will see that the coordination number times the exchange constant becomes a natural scale to use in our analysis. So I am going to study the phase diagram in the T by Zj, delta by Zj plane, right. Okay. And I will first study the phase diagram when H is equal to 0. So there is no symmetry breaking field of any kind. Okay. Alright. So first thing you have to check is what happens when delta equal to 0. If delta were 0, then this is the Ising model in disguise. I mean, there is one extra 0 state, but it will not do much. And what happens is you will get a continuous phase transition at T lambda. I am now going to call this phase transition point the lambda transition point, and that turns out to be, instead of Zj for the, if I had a two state Ising model, spin half Ising model if you wish, I would have got answer Zj, but now I get 2 by 3 Zj. Okay, that is also not surprising, no, because if I have more states, I prefer the disordered state and so on, right. So okay. Alright. Now if delta is a small quantity, now small quantity compared to J, let us say Zj, then you will see that the lambda, you will find numerically when you solve this, you will find that T lambda will be below this. But this is exactly what we had seen in experiment, that when you add a little bit of, when I add, remember what is delta? Delta is related to the difference of chemical potentials of mu3 and mu4. So if I increase delta, I am sort of increasing chemical potential of mu3, right. This is what I am doing. So I am increasing the concentration of X, I am increasing X. Okay. So I have the full set of results here. So these are a set of busy graphs here, and I hope I will be able to convey the main ideas here. Okay. So what I am showing you here is a plot of M. So that is the magnetization. So let us start with the point that we already had discussed. So if I start with delta by Zj equal to 0 and I go up in temperature, I have a finite magnetization which says that I am in a superfluid state. Remember, if I get expectation value of S, then I am in the superfluid state. So at this 2 by 3 0.6 something, you will see that the magnetization vanishes and this M goes to 0. Now when I increase delta, I will see that I have reduced the transition temperature, but I will have a continuous phase transition. But the important point is this does not go on forever. What you will find is there is a delta critical, which is what I am showing here, and the delta critical is something like 0.47 Zg, at which the line of continuous transitions stops, and that is this red dot, and the subsequent transition for delta values greater than this. So for example, if I take delta equal to 0.6 and go up here, you will see that there is a phase transition, but that phase transition is first order. So what I have in this phase diagram is a line of continuous transitions which ends and a line of first order transition begins. So I have a kind of interesting point where a line of first order transition meets a line of second order transitions. Okay. This plot here is a 3-dimensional plot of this result. So you can see that T by J is sort of starting from 0 here and going up here, and delta by J is starting from, so it is sort of viewing this picture from some top direction. So you will see that that is the line of continuous transition, and from here onwards it is first order, and that is what you see here. So this is the magnetization, and it tells us that the superfluid transition is sort of what we get here. So there is a regime of delta where it is second order, and there is a regime of delta where it is first order, and there is some interesting point that is where that meeting point of first order line and second order line takes place. Okay. But we should also now look for this phase separation of the miscibility gap that we know from experiments. So what I am plotting here in this graph is the fraction of helium 4, I am plotting x, which is the fraction of helium 3, and what you find is when when delta is very small compared to Zj, you will see that there are no helium 3 atoms. So if you look at, no meaning that there are very few helium 3 atoms. So if you look at this, you will see that the helium 3 atoms are sort of increasing very little here. So you will see how this is all helium 4 rich region. So this is helium 4 rich region, and after you have encountered this phase transition, if you sort of look at what happens in the X thing, you will see that there is this dome like feature that you see here. That means that at this value of T and delta, there are two possible solutions with different values of X, right. So there is one with a small value of X, which is helium 4 rich, and there is one with a very large value of X, which is helium 3 rich. And that is, so if you view this 3-dimensional plot from this direction, like for example Tx plane, hopefully you will see that there is this continuous line that is coming, that is the lambda transition, and this is like the split in this plot, and that is this miscibility gap. So you can see that this very simple model constructed out of spin 1 particles is able to get this phase diagram, at least qualitatively it looks very appealing, right. Okay. So this is the point. When delta is greater than delta C, as we discussed, you get this miscibility gap, and you are able to reproduce the phase diagram. Okay. So this is the story when H is equal to 0. Now because we are curious physicists, we will also like to know what happens if H is non-zero. So what I request you to do is to pause the video and try to see, based on everything that we have done before, can you guess what will be the change in these plots when I have H not equal to 0. So, immediate questions will be, will these continuous phase transitions survive, will this first order phase transition survive, etc. Okay. Alright. So, if you guess that all the continuous transition lines, the line of continuous transition simply go away. So, once you turn on this external field, as we know that that continuous transition in the Ising model will simply go away. So, you remember that I hope you realize that on this side of the phase diagram, this is more or less just a simple Ising model. So, once you turn on a field, you cannot have a continuous phase. So, you see immediately that the continuous phase transition goes away. However, there is a point on this phase diagram which is a continuous, which is a critical point where there is a continuous phase transition happening. What is that? So, you see there is this first order line that we had. So, the first order line ends at some point, and that point here, the point which I am showing by this little pointer here, that point is a point of continuous phase transition. So, if you go through this, if you increase the temperature through that point, then you will encounter a continuous phase transition. So, what happens at finite h is, there is a line of first order transitions that is ending in a critical point. In that critical point is quite similar to like the critical point that we encountered in the Ising system or the liquid gas system. Okay? And you can see the 3D plot shows this very nicely. So, this is a plot of the magnetization, and you can see that if my delta is small and I change T by J, you see that M just comes down continuously. There is no place where it suddenly becomes 0 and remains 0, right. There is no order parameter developing or dying above a temperature or something. Okay. And you can see that the miscibility gap etc. will persist, and you will get something like this, but the important point is that there is no continuous transition line here. There is one point where there will be a continuous transition. So, that you can sort of see here. So, you will come in here and then it will go to 0. Okay. So, this is the physics that we see at finite h. So, you can now legitimately ask like, what is the big deal of this, right? Okay. So, the big picture is the following. Okay, I am sorry to inflict my handwriting on you, but this is the figure that you will get. So, let me walk you through this. So, I have 3 axes here. There is the delta axis, T axis, this is what we have seen, and then there is the H axis. So, first let me see what happens on the T delta plane. On the T delta plane, there is a line of continuous transition which ends at some point, and then you get a first order line. Okay. Now, if you go finite h, then you know that there is this line of continuous transition does not exist, but there is a line of first order transitions which will end at a critical point. So, what you will end up getting is, you will end up getting 3 planes of first order transitions. What are the 3 planes of first order transition? This plane which I am showing here by this hatched thing here, that is a plane of first order transition similar to what happens in the standard Ising model when I apply a magnetic field. Magnetic field positive will give me plus polarized state, magnetic field negative will give me negative polarized state, and then there is a first order transition. So, that plane is a first order line, and that first order plane ends in the line of critical points. Quite similarly, there is a line of there is a plane of first order transition. This plane is the locus of the lines of first order transition that is realized for any finite value of h. This is like the one that if I go along this line, for example, that will be like the line that I showed you on the previous slide. Okay, and that will end in a critical point, which is also something that we saw on the last slide. And similarly, the same thing will happen when you have h negative. So, you will have similar stuff coming from there. So, now you see, you will realize that this point C is a very special point. What is special about it? To determine C, you have to fix 3 parameters, namely T, delta and H. Okay. So, the first order line at H is equal to 0 is where 3 first order planes meet. This is my point. You see, there is this first order plane on the TZ on the T delta plane, then there is this first order plane which is the H positive first order plane, some surface, it may not be a flat plane, and there is another first order plane for H negative. Those 3 will meet on this first order line which is on the T delta plane. So, now you realize that line is a line of triple points. Why is it triple points? You see, on that first order line 3 phases coexist. There is this plus magnetized phase, minus magnetized phase and this other phase, the 0 phase, they coexist. So, it is a line of triple points. Okay. So, you see the advantage of adding this magnetic field. We are able to discover that that line is a line of triple points. Most interestingly, this line of triple points will end, and at the point where it ends 3 second order lines will come and meet, right. That is a second order line, that is a second order line, continuous line, that is a continuous line, they will come and meet, and such a critical point where all this stuff is happening, 3 coupling constants are fixed, etc., is called a tricritical point, and it has its own set of interesting universal properties and so on. Okay. So, the tricritical point requires fixing of 3 parameters, and this is something that we have just seen. Okay. So, I hope you realize that from this very simple model we have been able to extract such a rich phase diagram. In fact, the surprise that we are experiencing was also experienced by the authors themselves. So, I have quoted from the paper and I will just read it for you. Indeed, it is somewhat surprising that a model as simple as this one, as simple as the one we have discussed, bears so close a resemblance as it does to the situation observed experimentally. The assessment may be, the agreement may be entirely fortuitous, but we would like to suppose that our approach has succeeded in including some essential physics. So, this is indeed a good lesson for all of us, in the sense that sometimes you can think about the physics of the problem and you can come up with simple models that can capture apparently complicated looking physics. So, friends, it is also important to realize that what helped us arrive at all these results is mean field theory. So, if you compute the critical exponents about this tricritical point, you will get some answers also. You can use the mean field theory to do that, but they may not match experiments. But the point is, you can access non-perturbative regimes, and in particular you can isolate phases and the boundaries of where phase transition take place and the nature of the boundaries. So, for example, this line here we now realize is a tricritical, it is a line of triple points, and this critical point is a tricritical point. So, all of these things you can get from using mean field theory. Okay. Okay, so we have had a fairly long chapter where we discussed approximate methods. So, let me just give you a summary of the chapter. So, approximate methods are needed to access non-perturbative regimes. So, this is for sure. So, Feynman variational approach is a nice, it's a sound approach, but the question is, how are we going to find these trial Hamiltonians? If you do not have some information from experiments or some other intuition, it is difficult to apply in practice in general. Mean field theory is the method of choice. The idea is to decompose product of fluctuating terms into mean fields, etc., and to self consistently evaluate these mean fields. Mean field theory is easy to apply in the sense that when you look at something, there are natural ways to find different decompositions into mean field, and you could, if you have some physical intuition as well, that you can use that physical intuition to choose a particular form of the mean field decomposition. Very important message that we got is that mean field theory will generally work better in higher dimensions. And we also got some physics gyan, if I might add. So, liquid gas has some deep connection to the Ising model. So, this is a very interesting qualitative idea that we have learnt in this course. We briefly looked at systems with continuous symmetry, and we argued that condensation of bosons can be modeled by breaking of a continuous symmetry with a complex order parameter. And very importantly, you can, starting from very simple models, you can get very rich phase diagrams, and you can use variety of techniques that we have used, that we have developed in this chapter to study many different problems. For example, the way we have discussed mean field theory, with very minimal change you can apply them to quantum problems, and you can model many current systems, twisted bilayer graphene, any of these systems you can use mean field theory to try and get some handle on what are seen experimentally and so on. So, my point is that the tools that we have discussed in this chapter are actually very useful and practically important tools. So, where do we go from here? So far we have used microscopic models, in the sense that we have started some arena, we have put in some lattice, we have put in some degrees of freedom, etc. Right. So, what we are going to do in the next chapter is we are going to discuss phenomenological theories. So, what we are going to take a different approach. We are going to look at, let us say, experiments, and we are going to see what we see in the experiment directly without worrying about what are the ultraviolet or the smallest length scale degrees of freedom, and we are going to write down phenomenological theories based on what we are observing. So, I am sure that phenomenological theories are something that you will definitely want to know about. So, please join me for the next lecture. Thank you.